Welcome back. Today we're going to talk about center of mass. Up until this point we've been studying motion and making an assumption that I don't know that we really thought about it a whole lot, but we made the assumption that all of our objects really were concentrated into a single particle. Now we're going to start looking at systems where the objects are not single particles, they can be distributed masses. In other words, they can be real objects and not just point particles. So we're going to learn some techniques for how to identify where that single point particle may be in an object that we want to deal with. Okay, where we can represent that oddly shaped object as a point. And we call that point, the location of that point, the center of mass. So let's go ahead and get started. Okay, so center mass of a system, and I'm talking a system, it can be more than one object, is the point at which all the mass can be assumed to reside. Okay, sometimes we call it the balance point. Okay, if you find the center of mass, that's where the object will balance. Sometimes a system is an assortment of particles, sometimes it's a solid object. And mathematically, you can think of it as the center of mass as the weighted average of the mass and their locations. In calculus, you called this, the technique was called the mean value theorem. So we'll be using that. It may be disguised in physics formula, but that's really what we're doing. We're using the mean value theorem. Okay, so assuming we have discrete points in our masses, individual little marbles, and we want to find the center mass of all the marbles. In the x dimension, we sum up the individual location of the marbles times their individual masses. And then we divide that by the total mass. You see, it's sort of like an average. We add them all up and then we divide by the number of them. But in this case, we're going to add up the product of their positions and masses and divide it by the total mass. So it's a weighted average of the location of the mass. And similarly in the y direction and in the z direction. If we have all three of those, we can identify the location of the center mass in 3 dimensions. Okay, there's also similar formulas for velocity and acceleration. For example, the x component of the velocity of the center of mass is the sum of the velocities of the product of the velocities with the mass of the individual little elements divided by the total mass. Now let's actually put this to work a little bit and try to put those equations into a form that maybe makes a little bit more sense to us. So we have 3 points, and I want to find the center of mass. I'm going to find the center of mass in the x direction first, or along the x-axis. And that's the sum of the position of each mass times that mass over the total mass. Well, what that means is particle number 1 here. What is the location of its x-coordinate? Well, it's at 0. So it would be 0 times its mass of 1 plus particle 2. What's the location in the x direction of the second particle? Well, it's negative 1 times its mass, which is 2. Now we're going to add on the third particle. Well, the x-coordinate of the third particle is 2, and the mass of that particle is 3, divided by the total mass. 1 plus 2 plus 3 is 6. So let's go ahead and tally this up. 0 minus 2 plus 6, so that's 4 over 6, or 2/3. So right here, that's where the x component of the center of mass is. That means the balance point is going to lie somewhere on this dotted line. Now let's do a similar thing for our y component of the center of mass. Okay, so the y component of the first particle, or the y coordinate, is -2 times the mass, which is 1, plus the y coordinate of second particle times its mass, plus the y coordinate of the third particle times its mass, divided by the total mass. Well, that's still 6. Okay, so what we have -2 plus 4, so we're at 2, minus 3, well, that's -1, so -1/6. Okay, so that's going to be somewhere up here. So the intersection of these 2 points is where this system's center of mass is. Okay, so center of mass is located at 2/3 minus 1/6. And I don't know what the units are, but let's just say, so I feel better about including units with this, that it's in meters. Okay, so that's 3 particles. Distinct, discrete particles, finding the center of mass of those is really easy. Okay, a little bit more complicated is if we have solid objects. Now, solid objects are not all that tough as long as their density is uniform. That means that they don't change their density as you move across them. That means that they are solid and made of the same material all the way through. There's no air pockets. There's no foam in the middle. Anything like that. Okay, or if, say, it's a ruler, it doesn't get thinner as you go to the edge. If it did, it would not have uniform density or uniform mass distribution. Okay, so this is really easy. It's the geometric center of the object. The center of mass for a solid object, if it's uniform density, is its geometric center. So for the simple geometric objects that we know, like circles, squares, rectangles, triangles, it's pretty easy to find their center of mass. If you have a combination of 2 of them, you find the center of mass of the individual component. For example, this disk, the center of mass of that is at the geometric center. That becomes the center of mass of a point particle representing the disk. And this rod here, or rectangle, the center of mass is the center of the rectangle. We add, to find the center of mass of this composite system, we use these 2 points as if they were point particles and add up the center of mass using the formulas like we did in the last example. We can shorten our work sometimes if we use symmetry. We can see that these 2 objects are symmetrical about the y-axis. Okay. Well, what that means is that the location of the center of mass, the x-coordinate of the center of mass, is at x equals 0. Just saves one calculation. Okay. Well, let's go look at an example. This is a little bit more complicated, but it'll help me introduce some ideas. We have this disk with a hole in it, and we want to find out the center of mass of that holy disk. Okay? Well, one of the things, mass, I have a geometric object here. How can we represent mass in our formula? I don't know what the mass of the objects are. Well, what's proportional to the mass? Well, I think it's either the volume is proportional to mass, or in this case, since we're looking at a two-dimensional object and we're going to assume that it has a uniform thickness, that we can use the surface area to be proportional to our mass, and that'll help us out. So I'm going to say area, I'll even put an S in front of it to make surface area, is proportional to mass. Well, what that says is the mass of this big disk, and let's assume that the cutout is still there, that we put the piece back in. So the mass of the composite, the two of them together, is proportional to the area of this whole big disk, which is pi r squared, but in this case our r is 2r, so it's 4r squared. Now it's not pi, 4r squared. Pi 4r squared. Okay, now how about this little missing part? I'm just going to call that mass of the whole. Okay, so, well, what's the radius of this? Well, it's r, so that'd be pi r squared. Okay, so recall that the center of mass formula is the sum of the masses times their locations over the total mass. Okay, well, I'm going to basically do a subtraction. This is a negative mass. You can think of it that way. What about the y direction? Do we have to worry about that? Symmetry. So we can automatically write down that the center of mass in the y direction is 0. Okay, let's deal with the x because that's the more important. So I have the composite, which is, where is the center of mass of the composite? Well, it would be right here, right at the center. So it's going to be 0 times the mass, which is 4 pi r squared, minus the mass, or the location times the mass. Well, this has a location of minus 1r, times its okay, and this is going to be all over the sum of the masses. Well, the first mass is 4 pi r squared, and the total mass, or the mass of this whole, we have to subtract, which is pi r squared, and we add this up, okay, and we have r times pi r squared. I know I could combine those, but I'm not going to, over 4 pi r squared minus pi r squared, which is 3 pi r squared. Well, those pi r squareds cancel, so the center of mass in the x direction is r over 3. And does that make sense? Well, I think it does. It's right about here, right where we would expect. Okay? So use a little reasoning and we can come up with solutions to problems like that. Here's a multiple choice problem. Good luck. Welcome back. Okay, so in the real world, shapes are not uniform and nicely symmetric, geometric easy shapes, so we have to deal with things that are more complicated. So let's take a look at the idea behind that. Well, for discrete simple points, we just add up the location of the center of mass of the object, of the simple object, times its mass divided by the total mass. Okay. Now we're going to turn this into calculus, because we're going to deal with masses that change with location or have odd shapes, so we can't use those simple geometrics. So now we're going to infinitesimalize it, differentialize it. We're going to take the location times an individual little mass element divided by the total mass. This should look a little bit like the mean value theorem. Now, here's a problem. We could do this just knowing what we know about symmetry and geometry. We could say that the center of mass of this object is right here in its geometric center, which is L over 2. We're not going to do that. We're going to do it the hard way. Okay, we're going to use calculus. Okay, so we have a long thin rod. The density, the mass, is a function of its length. So I'm going to use linear density. Lambda is equal to the mass per unit length. If I wanted to find out how much mass this entire rod had, I would take the density times the length, and that would give me the mass. Now, I need to add up little tiny slices, so I need to turn this into a differential. Okay, so lambda is equal to the little tiny masses, dm's, divided by the little tiny lengths. And because we're working along the x-axis, I'm going to call those dx's. Okay, so that would be, let's say, for example, this little yellow slice here. It has a mass is equal to dm, and the position, okay, or the size of it is dx. Okay? We'll say L equals dx. Okay. Now, I think we're ready to start. So the center of mass in the x direction is equal to the integral of x dm over mass. Okay, well, integral of x, and we're going to take that, the limits, I'm going to put limits on it, right? We're going for x equals 0 to x equals L, 0 to L. Okay, and dm from this step right here is equal to lambda dx. All over the total mass. Okay, well, what's the total mass equal to? Well, the total mass is equal to lambda times L. And that's what the mass is equal to. So I'm going to plop that in right here. Let's put it in the right order. Lambda L. Okay, so uniform density means that lambda is a constant. Okay, so I can take lambda outside the integral. I can cancel them both out because they appear top and bottom. And now I'm left with a fairly simple integral. So the integral of x with respect to x is x squared over 2. L is there, and we're going to evaluate from 0 to L. Okay, so when we evaluate it, we end up with L squared over 2L minus 0 over 2L, and that's equal to 0 goes away. It's L squared over 2L. Get rid of one of those L's, and we end up with L over 2. Agreement! Woohoo! Okay? Kind of weird. You probably haven't looked at calculus like this, but it's the wave of the future. So you'll see a lot more of this kind of weird stuff in the next few weeks. Well, this is one that's a little bit different, and I promise this is the last slide of the video, and we've already did most of the work. Okay, so in this case, we were given a function for lambda. Lambda is not a constant. You can see in the shading of the bar, it gets more dense as it comes out to the end. Okay, so lambda still equals dm over dx. Okay, well, lambda is alpha x, so alpha x is equal to dm dx. Well, that means that dm is equal to alpha x dx. And what's mass equal to? Well, if we were to take the integral of both sides, that would give us our mass. Okay, we'll have to do that a little bit later on. So for now, I'm going to take those away so we don't get confused. So the center of mass in the x direction. That was a funky way of writing that. X, center of mass, is equal to the integral of x dm over the total mass. Well, x, the integral of x dm, here's dm, is alpha x dx over the total mass. I know we need to do some more work down here, but I want to get the top side done first. And we're going to integrate from 0 to L. Let's go ahead and collect some things together. Alpha is a constant, move it outside. Integral from 0 to L, well, x times x is x squared dx over big M. Okay, moving on down. So the integral of x squared is x cubed, okay, over 3 times alpha, evaluated from 0 to L, over M. So this is equal to alpha L cubed over 3 over the total mass. We don't know what the total mass is, but we know how to find it out. We're going to use this right here. So dm is equal to alpha x dx. We're going to take the integral of both sides. We're going to evaluate the mass from 0 to the total mass, and this from 0 to a length of L. So on the left-hand side, we just get M. Usually we're going to skip this step here and just go right to what it is. Okay, alpha is a constant. Our integral of x is x squared over 2, evaluated from 0 to L. So the mass is equal to alpha L squared over 2. Now let's go ahead and plug that back in here for our mass. Okay, so we have alpha L cubed over 3 all over alpha L squared over 2. Well, we can get rid of an L squared and another L squared on the top, leaving behind an L. We can get rid of the alphas. So now we have L over 3 over 2. And that gives us, I'm going to move over here. I don't plan out my space usage very well, I guess. So the center of mass of that rod is 2L over 3. Does that make sense? Well, where is it heaviest? Is it heaviest here or is it heaviest out here? Well, it's heaviest out here, so it's going to favor, the center of mass is going to be more to the heavier side. So at 2/3 L, okay, that works for me. That makes sense to me. Okay? So this is how we can use that calculus stuff to find out an answer to a problem that's of interest. Unfortunately, most of the problems that are of interest are not simple like this. But that's for another day. Okay, moving on. And here's your free response question. Good luck. We'll see you next time.